Okay. Where are you?
Mrs. Lehman said that I could go down. She just
Okay. All right. Sounds good. Thank you.
Yep.
Okay. So I'm going to talk about mixtures here. One of we've got different types of mixtures that we're working with, and this chapter is on mixtures and solutions particularly, and we're going to get into something called molarity. And if you take AP Chem, we use molarity a lot, and this is also going to feed into the concentration of acids and bases as well, which is our next unit. So what I have planned out for us for the rest of the year is this chapter and then the acid base chapter as well. So I want to get through this chapter. This chapter has an online lab component to it with that pivot lab simulation. And then it also has, we're going to do a serial dilution lab where we're diluting solutions down and learning how to make solutions from like powder and that sort of thing. That's the stuff actually comes in a powder form for most of the chemicals that we use here. And then we have to create that and use that for your labs. We do that in the back room usually before you guys come in. But it's a key concept that you've got to know for AP Chem. It comes up notoriously every year on the AP Chem exam. So molarity feeds into with this unit, and then we'll do the acid base unit, and I want to get a titration in on that as well, so we can get you going with the burettes and that sort of thing. So there's different types of mixtures. One kind is a suspension, and this is where particles are going to settle out over time. So like if you had clay and water and it was mixed together, okay, you could stir it up and make it work, but over time that clay is going to sink back down to the bottom. Okay. Then we have these thixotrophic mixtures, and when these are agitated, it's going to flow like a liquid, but when it's left undisturbed, it's hard. So like cornstarch and water is a good example of this. There are also thixotrophic soil out there. And so people have to be careful when they're building different structures. They've got to check and make sure that they're not building in an area that has this, because that's an earthquake zone particularly, okay? Because if you're working and you're in a situation here where your foundation is built on something like this, and then you get this shaking of the earth, that thing starts to flow like a liquid, there goes your foundation. And so this is something that engineers and builders have to be aware of to make sure that they're not building in a type of place like this. And if you've ever played with cornstarch and water, it's kind of a fun, like it flows. This is your oobleck and glurch. So when you guys did oobleck and glurch back in the day, if you ever remember that, this was one of those, either depending on what your teacher called it. Okay, colloids then, they are intermediate sized particles. They don't settle out over time, and they tend to be categorized by their phases. And remember, we talked about these in terms of a Tyndall effect. This was back in chapter 3 where we talked about the Tyndall effect, or if we shone a light beam through it, it's going to internally reflect within this colloid. The suspension, it will also do it, but remember the suspension is going to settle out over time, and then the light beam will go through. So, so the colloids, it's going to be positive for that Tyndall effect. I talked to you guys about fog and like why you don't use your high beams in the fog. Do you remember me talking about that back in the day? So fog is actually a colloid. And if you shine your high beams in, or your brights, whatever you want to call them, if you shine those into that fog, it's going to internally reflect that light and shine it back in your eyes, and it actually makes the fog worse. That's why when you're driving in fog, you always want to make sure that you're using your low beams, or I don't know what they call low beams, not brights, but regular, I don't know. Anyway, but you don't want to use your brights when you're in fog, because that's a colloid and it can cause a problem. We have something called Brownian movement here. It's this erratic movement of these colloid particles. They're going to be dispersed within the material, and they're resulting from the collisions of the particles, and they help to prevent the colloid particles from settling out. So this Brownian movement causes that. Let me see if I can find this video here. I know the sound won't work for the folks at home, but I don't think there's really sound on it anyway, so. So that was kind of the Brownian movement there. You can see this is the Brownian movement that we're trying to get past to you. So it's just a random kind of movement. They're bumping into particles. They're bumping into each other. So that's your random Brownian movement. It's just this random colliding and collision. Okay. Let's get back over here. We talked about the Tyndall effect. Jello is also a Tyndall, or is also a colloid, if you're familiar with Jello. All right, vocab review. We talked about these back again. We talked about these in chapter 3, I believe. We have a solute, that's the substance that's getting dissolved. We have a solvent that's doing the dissolving. So if we had salt water, what's the solute in salt water? Salt, and then the water would be the solvent. Okay? The thing collectively together, once these are mixed together, is called a solution. Yep. Okay? And it's going to be key that you're able to identify these three distinctions, okay? Solute, solvent, and solution. Because parts of the math that we're going to do tomorrow, sometimes you divide different parts of this. So it'll be like the moles of this divided by the liters of the solution. Sometimes it's going to be this divided by this. So you've got to pay attention and make sure that you understand what part of that formula you're going to be working with, or what component here you're working with. All right, these solutions do not separate over time. They can be solids, like our alloys are examples of this, where you have like bronze. They have, or brass, so like copper and zinc alloyed together, mixed together, that's going to cause, and that's going to create an alloy of brass. Liquids, we can have liquid solutions mixed together, like rubbing alcohol and water. I did that demo in here with you guys, or I showed you the demo that they did, Bill Nye did, with the alcohol and the water. And then you can have solutions of gases. So what we're sitting in right now is a solution of gas. Okay, there's carbon dioxide in the air, there's oxygen in the air, there's other stuff in the air. That's a solution. Now, if we see that the sky is all smoky, that's not a solution anymore. Okay, those smoke particles are going to settle out over time. They're bigger. And that would be like a suspension. Most solutions are liquids, so keep that in mind. Okay, So we don't have a lot of these. We don't have a lot of these that we deal with in here anyway. So most of them we're going to be focusing on this. All right, here's a table that shows you kind of examples of this, like air, for example. Gas and a liquid, this would be like your POP, where you have water and gas combined. Gas and a liquid, again, ocean water, the oxygen that the fish breathe in water is actually dissolved in that water, okay? So common misconception that people have is that the fish take the water molecule and chemically break the oxygen off. That's not what happens. What happens is, let me see if I can find a picture of this. Oxygen dissolved in water diagram. Here we go. Already, it's always better to kind of show. Okay, so these people do better drawings than I do. All right, so what happens is you've got, you know, that still isn't a good one. Here we go. All right, so here you've got your water molecules here, and then you've got your oxygen molecules, and they're dissolved in here, okay? So that's what's going on, is you've got the oxygen dissolved in here. They're not going, the fish don't take the oxygen off of the water and break that off and use it. They use this dissolved oxygen. Now, interestingly, as for gases, the solubility of a gas goes down as the temperature goes up. So that's why you like to drink cold pop. I mean, it's refreshing, but it also holds on to more of the carbon dioxide dissolved in there. So if you have pop that's warm, it's going to go flat much faster because the solution can't hold that gas in. It's incapable of doing that. And so that carbon dioxide gas comes out of solution. Okay, so that is a gas and a liquid. Liquid and a liquid would be like antifreeze, vinegar, ocean water. Solid and a liquid, you've got sodium chloride that's dissolved in there. And then liquid in this, silver. They don't use mercury much in that anymore. And then I talked to you guys about bronze as well. Okay, so soluble versus insoluble. All right, so soluble versus insoluble. So something that's soluble would be able to stay mixed in, so like sugar and water, and something that's insoluble won't stay mixed in, like sand and water. You could also have some insolubility issues due to polarity, like with oils. Okay, so you'd have two liquids mixed together, but the oil isn't going to stay mixed in, and that has to do with the oil being nonpolar and the water being polar. The polar molecules of the water are going to stick together and not allow that nonpolar water or oil inside there. Okay, they're not going to surround it. Now we have two more terms. So today's laden with vocabulary terms. We have two more terms. We have immiscible and miscible. This deals with liquids only. Okay. So if something is immiscible, that means two liquids are not soluble. They won't mix together. If something's miscible, then that means two liquids are mixed together. They are able to be soluble and able to mix together. So oil and water are immiscible. All right, so aqueous solutions. Aqueous means what?
Dissolved in water.
Water, exactly. Yep. So it's going to be dissolved in water. And what happens is we have this solvation. It's the process of the solute getting surrounded by these water molecules. And when this happens, it's called hydration. The attraction between the solvent and solute particles has to be greater than the attraction between just the solute particles. Let me see if I got a picture of this. Yeah, I do. Okay. I don't know. Did you have to write stuff in for this? You good? Okay. All right. So we've talked kind of briefly about salt water before. And the water, remember the water has these dipoles. It's got these positive and negative dipoles. And it's also constantly moving around. Okay. So this is kind of what happens when you've got your salt crystal here. So this is our sodium and our chlorine. Okay, chlorine's the green, sodium's the gray. You've got your water molecules. So your water molecules are going to come in. Remember, the red end of the water molecule here is negatively charged, and this end is going to be positively charged. So the positive ion is going to get surrounded by these water molecules. The negative ion is going to get surrounded by the positive end of the water molecule here. And what ends up happening is this water just keeps pulling these ions away because the attraction for the ion to the water is greater than the attraction of this ion to this ion. And over time, all of these ions get surrounded by water. That's one situation. Or you run out of water molecules to surround the ion. Okay? In a situation where everything is surrounded, then we call that unsaturated, if we have water left over. And in a situation where we have this stuff left over and no water left over, we call that saturated. So unsaturated, we have water left over. Saturated, we don't have any water left over. Does that make sense? All right. Good. All right. There is also another situation called supersaturated. And this is where you can heat up a solution, okay? Get a whole bunch of solute in there and then cool it back down. And that solute will stay in solution, but it is very, 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 what's the word? Unstable, okay? If you drop one crystal of that solute in there, it'll seize up and end up being a solid again. If you just take the flask and just kind of give it a good tap on the side, it'll seize up. That's how unstable it is. Okay, I have some of this back in the back that I can mix up. I just need to remember to do that. Let me write that down on my to-do list so I can show that to you guys. Sodium acetate. This doesn't happen with like every, excuse me. It doesn't happen with like every solute and water mixture. It's just certain ones. Sodium acetate is a good example of this. but that's an example. Okay, so here's what I mean by kind of seizing up. It would look clear as water initially, and then if you drop one crystal in there, it just all right, so that's all I'm doing for today. That's as far as the lecture notes are going to go for today. And then tomorrow we'll pick up with solution concentration, and that's where we're going to be doing a lot more math. Okay, so make sure you have a calculator handy.